Okay, physical chemistry, we're now beginning chapter 6. This is section 1. We're talking about reaction equilibrium in an ideal gas mixture. So, first let's say we just have a pure ideal gas. Our condition for reaction equilibrium is going to be the sum of mu sub I is equal to 0. We talked about that before. Remember, mu sub I is greater than 0 for products, mu sub I is less than 0 for reactants. Now remember, mu is a function of temperature and pressure, and it's an intensive state function. Now, we have the Gibbs equation. Remember, G is equal to SdT plus VdP, or if you divide that by N and get the molar form, then you have dGm is equal to minus SmDT plus VmDP. And this is for a pure ideal gas. Now, since we have a pure ideal gas, we can say d mu is equal to dGm. So we have d mu is equal to minus Sm dt plus Vm dP. And also that mu is equal to Gm. Now let's assume we have constant temperature. That obviously means that the differential of temperature is equal to 0. So this first term drops out. So we end up with d mu is equal to molar volume dP. Then using PV equals nRT to substitute out, we just get RT over P dP. Now we want to integrate that, so we get the integral from state 1 to state 2 of d mu, and that's equal to the integral from state 1 to state 2 of RT over P dP. R and T are constants. Remember, we said temperature was constant, so those will come out, so we just end up with natural log of pressure 2 over pressure 1. Now, integrating that just gives us mu at temperature and P2 minus mu of temperature and P1. And what we're basically going to say then is that our P1 is really P naught, or 1 bar. So this term is going to drop out. It's going to be equal to 0 or whatever we had. Or no, it's not going to be equal to 0. It's going to be our mu naught. Anyway, so then that's equal to RT ln P2 over P1 like we set up here. So then what we had then is mu of temperature at our pressure of interest is going to be equal to mu at naught. So mu at temperature of interest is equal to mu naught at temperature plus RT natural log of P over P naught. So this will give you a way to calculate mu if you're not at a normal state of 1 bar. Continuing on physical chemistry, chapter 6, section 1, we showed before how mu at temperature is equal to mu at temperature naught plus RT natural log of pressure over pressure naught. Now look at this graph here. We're counting from 1, 2, 3, and then 0 to RT, 2RT, minus 2RT, etc. So what this is showing us is that as pressure approaches 0, our mu is going to go to minus infinity. So this is pressure, this is mu. So mu, we also know, is equal to Gm, which is equal to Hm minus Tsm. Now remember, Hm is independent of pressure. It's dependent on temperature only for an ideal gas. And molar Sm is equal to molar Sm as a function of pressure. Okay, now let's talk about what if we have an ideal gas mixture. Now we know that PV is equal to nRT for an ideal gas. That's total pressure times volume is equal to the total number of molecules times R times T. But for each substance I, we know that the partial pressure is equal to the mole fraction of I times P total. Remember, this is not xi, this is X subscript I. So mu I is equal to the chemical potential of the gas in the mixture, but mu I star is equal to the chemical potential of that pure gas I in equilibrium with the mixture. To understand what that means, look at our system here. We have it divided in 2 parts by a membrane that will only pass substance I. On the left side, we have only pure substance I, and that's at pressure I star T. But over here, we have our ideal gas mixture, I and possibly other substances. So over here, the pressure of I is equal to mole fraction of I times P total. This, like I said, is our ideal gas mixture. Physical chemistry, chapter 6, we're finishing up section 1 now. So remember that diagram on the previous slide. So at equilibrium, we know that the pressure of substance I star, that's the pure substance, is equal to the partial pressure of substance I in the mixture. Or another way to put that would be that the chemical potential of I in the mixture is equal to the chemical potential I star, which means pure. Now we know that mu sub I is a function of temperature and pressure, the mole fraction of 1, mole fraction 2, etc., all the way to mole fraction of I. And that's equal then by this to mu sub I star of temperature and x of I times P total. And this simplifies to just mu I star, temperature times the partial pressure of substance I. Now remember, Pi star is equal to mole fraction I times P total, since we're assuming no intermolecular attractions. Remember, we're still dealing with the ideal gases. So mu I star as a function of temperature and partial pressure of I is equal to mu I naught, temperature, plus RT, natural log, partial pressure of substance I divided by P naught. And remember, P naught we said was 1 bar. So for the mixture, mu sub I is equal to mu sub I naught plus RT, natural log of Pi over Pi naught. For physical chemistry, chapter 6, we're starting section 2 now. We're talking about ideal gas reaction equilibrium now. So we have mu I is equal to mu I naught, which is dependent on temperature, plus RT natural log of Pi over P naught. So remember, I is the substance, naught means our standard state, and then P is the partial pressure of substance I, and P naught is the pressure 1 bar at standard state. Remember, we have to divide inside the natural log because we need a dimensionless quantity in there. You can't take natural log of a dimension. We also know that the sum of mu I is equal to 0. Remember, mu I is the stoichiometric coefficient, and mu I is the chemical potential of the substance. And it'll be positive for all the products and negative for all the reactants. Now remember, mu is dependent on both temperature and pressure. Now we're going to have the sum of mu I then. It could be rewritten as the sum of mu I times all this up here we're substituting in. So we have mu I naught plus RT, natural log of Pi equilibrium divided by P naught. So that'll be the partial pressure when we're actually at equilibrium. And this is going to be equal to 0 when you're at equilibrium. So we have the sum of mu I, again this is stoichiometric coefficient, chemical potential, sum over all substances I. So that's going to be equal to the sum. We're distributing out the sums. We're splitting this apart into 2 separate sums here. So we have one sum, mu I, not a function of temperature, dependent on temperature, which we didn't explicitly show earlier. And then plus another sum, RT sigma mu I, natural log of partial pressure of I at equilibrium divided by P naught, 1 bar. Now, we know if you have the pure component, then the chemical potential for I is just the same as the molar Gibbs free energy. So, substituting that in, we could say that mu I naught at temperature is equal to the change in the Gibbs free energy, molar energy. And remember, the naught means you're at standard state, which is at 1 bar. Now, substitute that in, we're going to know that delta GT naught is equal to the sum of mu I naught as a function of temperature. And then substituting in what we had before, then we have delta GT naught plus RT, the sum of mu I, natural log of Pi, partial pressure at equilibrium divided by P naught is equal to 0. Now we're going to, substitute that in again here. What should we do? Oh yeah, so this is equal to 0 like we had it before, and we're going to get these on opposite sides by subtracting this. So we have delta GT naught is equal to minus RT times the sum of mu I, natural log of Pi equilibrium divided by P naught. But then we're going to move this inside the natural log, which is an exponent. That's just a rule of natural log and exponents. So then we have delta GT naught is equal to minus RT times the sum of natural log, the partial pressure at equilibrium for each substance I divided by 1 bar to the stoichiometric coefficient power. And remember, we'll still have positive for product and negative for reactants here. Continuing on physical chemistry, chapter 6, we're in section 2 now. Remember, just like we have a sigma for summation notation, we have a capital pi to mean product notation. We're going to be using this here. Also remember your rule of natural log and exponents. If you have natural log of A plus natural log of B, natural log of C, that's the same as the natural log of A times B times C. So we know from before that delta G of T naught is equal to minus RT times the sum of natural log of the partial pressure of substance I at equilibrium divided by the standard pressure of 1 bar to the nu I power, where nu is the stoichiometric coefficient. So we're going to replace the summation notation with product notation. So we then just have, oops, that should be a minus, shouldn't it? Hold on. Okay, so anyway, we have minus RT natural log of the product of these partial pressures. See how there's a sigma on the outside, product on the inside. So we have the partial pressure of substance I at equilibrium divided by P naught to the nu I power, where nu I is the stoichiometric coefficient. So what we're going to do is we're going to take that product and give it a name called Kp naught. K, of course, would be constant, P is pressure, and naught means standard pressure, or 1 bar. So this is called the standard pressure equilibrium constant. And it's just the summation I already told you. It's the product. Yeah, I said sum, I meant product. The product over substance I of all partial pressure of substance I at equilibrium divided by 1 bar times the nu I power. So then we can just rewrite what we had above as delta G naught as minus RT times the natural log of Kp naught. If we take this and just algebraically solve for Kp naught then, we also know that Kp naught is equal to E to the minus delta G over RT. Now, for example, let's do the same reaction we've been using over and over. Nitrogen plus hydrogen to get ammonia. So notice 1, 3, and 2. Positive, negative. So Kp naught is going to be the partial pressure of the ammonia at equilibrium divided by P naught squared because of the 2 times the partial pressure of the hydrogen at equilibrium divided by P naught to the minus 3 because it's a reactant times the partial pressure of nitrogen at equilibrium divided by P naught to the minus 1 power because it's a reactant. So rewriting that in fraction, we get Kp naught is equal to the partial pressure of the ammonia divided by P naught squared, and all that's divided by the partial pressure of hydrogen at equilibrium divided by P naught cubed times the partial pressure of the nitrogen at equilibrium divided by P naught. Or if you can't remember all the rules for numbers, just put in the products over the reactants. Physical chemistry, chapter 6, continue on section 2. So we just showed how to find Kp naught. It should be obvious then that Kp naught is dimensionless because all the pressures are going to cancel out. On the other hand, we do have Kp, which is the pressure equilibrium constant. It's calculated the same way, except you're not going to be dividing by standard pressure. So you could end up with units of pressure depending on the details of the reaction. For example, using the same reaction, we have Kp. So we have the pressure of the ammonia squared divided by the pressure of nitrogen divided by the pressure of the hydrogen cubed. This is obviously ATM squared. This is obviously ATM. This is obviously ATM cubed. So that gives us 1 over ATM squared, or just ATM to the minus 2. So the Kp could have units of ATM, ATM squared, ATM cubed, whatever, just depending on the reaction. Kp naught is a function of temperature though. So let's say we have a generic reaction where A amount of A, B amount of B, in equilibrium with C, dt, etc. Then we have Kp naught, that would be the partial pressure of C divided by P naught to the C power, partial pressure of D divided by P naught to the D power, divided by the partial pressure of A divided by P naught to the A power, times the partial pressure of B divided by P naught to the B power. So it's just like I showed you on the previous slide, just put all the products on top and all the reactants on the bottom. Now we're also going to have an equilibrium constant for concentration, Kc naught, and we're also going to have one based on mole fraction, which will be just Kx. Notice there is no naught. Okay, continuing on physical chemistry, chapter 6, section 2, we were talking about the concentration equilibrium constant K sub C naught. Now, we know that the concentration of substance I is just the number of moles of substance I divided by the volume, total volume. So C sub I is the molar concentration of substance I, moles per volume. So using PV equals nRT, we know that the partial pressure of I is equal to the number of moles of I times RT divided by the total volume. And from up here then, we can say that's also equal to CI RT. Now let's use the generic reaction A of A and B going to F of F and D of D. We didn't use C and C again because we're using C for concentration now. That'd be confusing. So Kp naught, we're going to substitute in pressure from what we found up here, and instead we have C of F RT divided by P naught to the F power, C of D RT over P naught to the D power, C of A to the RT, or times RT to the, over P naught to the A power, and CV times RT over P naught to the B power. Now we also know then, again from up here then, that RT over P naught, that's equal to 1 over concentration, molar concentration at a substance, remember where the naught means standard state. So we're defining C naught as 1 mole per liter. And if you rearrange this, you'll notice that if you multiply R times T times the concentration, that you're going to end up with the same units that you used to measure pressure. So that's what we've done up here. We substituted in the pressure. Oh, now we've pulled out this. We've made it look like that. So we're going to have just concentrations. So Kp naught is just going to be the concentration of F divided by the standard concentration to the F power times the concentration of D divided by the standard concentration to the D power, and all that divided by C of A divided by C naught to the A power times C of B divided by C naught to the B power. And we've pulled all that out from up here, so we just have C naught RT over P naught, and then you just add up all the exponents, positive for products, minus for reactants. That is if you were finding Kp. Now this we want to get rid of because we don't want to talk about pressure, we just want to talk about concentration. So then what we're going to just define is Kc naught, and that's just going to be equal to the concentrations divided, exactly like we had for pressures before. Physical chemistry, chapter 6, continuing section 2. So we're going to find the change in the number of moles per mole by adding the exponents, positive for the products, minus for the reactants. Because we're dividing by mole, we're actually getting no units, so we can take exponents and stuff. Now we already saw that Kc naught is equal to the product of the concentration of each substance divided by the standard concentration to the new I power. And then likewise Kp naught is just Kc naught to the times RT C naught over P naught to the delta N per mole power. Remember, C naught we defined as 1 mole per liter. Temperature has to be in kelvins. Now, P naught we defined as 1 bar, or 0.897 atm. And we're going to probably use the R gas constant as 0.08206 liter atmospheres per mole kelvins. Kp naught, remember, is dependent on temperature. Kc naught is also dependent on temperature. Now, for an example, it is possible for a reaction to have delta N is equal to 0. For example, let's say we take some hydrogen iodine, or iodide actually, and it's in equilibrium with hydrogen gas and iodine gas. Then obviously 2 on 1 is 2, so delta N equals 0. And this only applies for gaseous components. Remember, we use P equals nRT to get this. Okay, now we're going to talk about another equilibrium constant, the mole fraction equilibrium constant, which is Kx. Kx is the product, just like we did before, but instead of concentrations, we're going to have mole fractions at equilibrium. But we're still going to take the exponent for each one. So to refresh your memory, then Kp naught, that'd be Kx times P over P naught to the delta N per mole, just substituting in. Now remember, the partial pressure of substance I is just equal to the mole fraction of substance I times P, where P is the total pressure of your system. Continuing on physical chemistry, chapter 6, section 6. Now we're going to do an isochoric addition of inert gas. Now remember, isochoric means constant volume, but we're also going to assume that temperature is constant. Now remember, the partial pressure of I is equal to the number of moles of I times RT over V, if you have a perfect gas, which we do. Pi is not changed by an inert gas. I mean, if you can add all the helium you want, it's not going to change the partial pressure of your stuff. So Qp remember, is equal to the product of Pi to the nu I power. So there is no shift in equilibrium. So what this tells us is that adding a noble gas or not has no effect on equilibrium. Now, let's say that we have a reactant gas. Then the temperature and volume are constant. So, we're assuming temperature and volume are constant. That's our first scenario. So A goes to A gas plus B gas, that goes to 2C gas plus D gas. So there's going to be a little bit of change in moles here. So our Qp at any time, remember, is Pc squared times Pd over Pa Pv. Just remember, it's products over reactants. And when we're at equilibrium, that's going to be equal to Kp. Now let's say we add some A. Well, since Pi equals Ni RT over V, just like we had before, that means adding some A increases Pa. But since A is a reactant, it's on the bottom, that's going to make Qp decrease. So now we have Qp is less than Kp. So what that means is that Qp is going to increase until Kp is equal to Kp again. Of course, for Qp to actually do that, you're going to end up with more products. Continuing physical chemistry, chapter 6, section 2. So if the change in the number of moles is 0, that's gas moles, remember, then Kp naught is equal to Kx, and both are dimensionless, they have no units. On the other hand, if the change in the number of molecules or moles is not equal to 0, remember just the gas phase ones, then Kx will have units. Kp naught will still be dimensionless because we divide by the pressure, standard pressure. Kp naught is more important than Kc naught or Kx. And delta G naught, we already showed, is minus RT natural log of Kp naught. But since K is the common one, then you could just say minus RT natural log of K. So we say that K is the thermodynamic equilibrium constant. And it's the same thing as Kp naught. Now remember, Kx is a function of both temperature and pressure. And Kc naught is equal to a function of temperature. And Kp naught is just a function of temperature only. So now we're going to have a little qualitative discussion of chemical equilibria. We know Kp naught has to be greater than or equal to 0, and it has to be less than infinity for any equilibrium. So the first case, what if Kp naught is really, really large? Well, then that means the products are favored and our reaction is effectively going to go to completion. The second case, what if Kp naught is much less than 1? It's very small. Then that means our reactants are favored. It's going to go to completion in the wrong direction. We're not going to get any product. And the third case, what if Kp naught is roughly equal to 1? Then that means the equilibrium is going to have substantial pressure, both the reactants and the products. So if you want either one, you're going to have to find a way to purify it. Unfortunately, this is the most common case. Now, we showed before already that delta G is equal to minus RT natural log of Kp naught. Solving for Kp naught then, getting rid of the minus exponent, we get 1 over e to the negative, or to the delta G naught divided by RT. This is physical chemistry, chapter 6. We're finishing up section 2 now. So we showed before delta G. Now, if delta G naught is much greater than 0, that means Kp naught is very small, so the reactants are favored. If delta G naught is less than 0, then we get Kp naught is very large, and the products are favored. If delta G is roughly equal to 0, then Kp naught is roughly equal to 1, and then you should expect both reactants and products in your equilibrium. Now we know from a long time ago that delta G naught is equal to delta H naught minus T delta S naught. That's assuming constant temperature, obviously. Now, if we have low temperature then, this pretty much disappears. So then we have the delta H naught term dominating. So delta G can be approximated by just saying it's equal to delta H naught. Because as temperature goes to zero, the change in the entropy of the change in the entropy of the reaction approaches zero also. So both this will disappear and this will disappear on you. Now at high temperature, minus T delta S naught, this is going to be very large because you're going to have a huge number for T. So this is going to dominate. So delta G can be approximated as just saying it's equal to minus T delta S naught. For example, the air I'm breathing right now, it's mostly nitrogen, diatomic. It's officially in equilibrium with 2N, but it's not happening for real. The reactant is favored. The reason is obvious. Nitrogen is triply bonded to itself. So it takes a huge amount of energy to break this bond. So we know that delta H naught is much greater than zero. So breaking this would be highly endothermic. Good luck doing that at room temperature. But at really high temperature, then we can get enough energy to break those bonds. We're in Physical Chemistry, Chapter 6, beginning Section 3 now. We're going to talk about the temperature dependence of equilibrium constant Kp naught. We already said several times before that Kp naught is a function of temperature only for an ideal gas. And we know that delta G naught is equal to minus RT times the natural log of Kp naught. So solving for natural log of Kp naught, we get natural log of Kp naught equals minus delta G over RT. Now we're going to find the derivative of this, and we don't know this yet, so we're going to have to use the chain rule. So we get the derivative of the natural log of Kp naught divided with respect to temperature is equal to delta G naught over RT squared minus 1 over RT times the derivative of the change in Gibbs free energy naught with respect to temperature. This is what we need to figure out now. So we know that the derivative with respect to temperature of delta G naught is equal to the derivative of, with respect to temperature, of the sum over I of nu I times the molar Gibbs free energy of all those substances I. And that can just be written then as the sum over I of nu I times the derivative of the Gibbs free energy molar for each substance I with respect to temperature. So that's going to give us the derivative of G molar for substance I with respect to T is equal to minus the entropy of the substance I, molar, at standard pressure, 1 bar, or the derivative of the change in Gibbs free energy, molar, naught, with respect to temperature, is equal to minus delta S, molar, naught. Now remember the Gibbs equation, we had dG equals Sm dt plus VdP. So in molar form, that would be the differential of molar Gibbs free energy is equal to minus the molar entropy times the differential of temperature plus the molar volume times the differential of pressure. So at constant pressure then, we can say that this whole term here is going to be equal to 0. So we're left with just the differential of molar Gibbs free energy is equal to minus molar entropy times the differential of temperature. So that is how we got minus S molar is equal to dG molar for substance I with respect to T, temperature. Continuing on Physical Chemistry, Chapter 6, Section 3 now. So we end up with the derivative of natural log of Kp naught with respect to temperature is equal to delta G naught plus T delta S naught over RT squared. And remember, G plus T delta S is delta H. So we just get delta H naught over RT squared. That equation is called the Van Hoff equation. And this shows us that Kp naught is dependent on delta H naught. Now we want to find the integral of that. So what we're going to do first, multiply by dt, so we have the t and the dt on the same side. So I get the differential, the natural log of Kp naught is equal to delta H naught over RT squared times the differential of t. Now we can integrate that. So we're going to have the definite integral from Kp naught of T1 to the Kp naught of T2 of the differential of natural log of Kp naught. And that's going to be equal to the definite integral from temperature 1 to temperature 2 of delta H naught over RT squared with respect to temperature. Then we're going to assume that delta H naught is a constant with temperature. So this side is just going to become the natural log of Kp naught of T2 over Kp naught of T1. Since we're assuming delta H naught is constant, this is going to be roughly equal to delta H naught over R times the integral from T1 to T2 of 1 over T squared with respect to T. So that's going to be delta H naught over R times 1 over T1 minus 1 over T2. If we switch these two around, then it becomes a minus sign. So it's like multiplying by minus 1 here and minus 1 there. So we get natural log of Kp naught of T2 over Kp naught of T1 is roughly equal to minus delta H naught over R times 1 over T2 minus 1 over T1. Then we want to get rid of the minus sign again. Oops, how did we do this? Hang on. Shoot. Oh, so we flip this upside down. We flip this upside down to get that'll be the minus of this one. So then we get natural log of Kp naught of temperature 1 over Kp naught of temperature 2 is roughly equal to delta H naught over R times 1 over T2 minus 1 over T1. This is called the integrated form of the Van Hoff equation. This is Physical Chemistry, Chapter 6. We're finishing up Section 3 now. Now remember, the derivative with respect to T of 1 over T is equal to minus 1 over T squared. Now doing algebra on that then, just multiplying by dt, we get differential of 1 over T is equal to minus 1 over T squared times the differential of T. Therefore, dt is equal to minus T squared d 1 over T. Now we're going to substitute that in to what we had before. Remember, we had derivative of natural log of Kp naught with respect to temperature is equal to delta H naught over RT squared. So substituting in that, we get the derivative of natural log of Kp naught over minus T squared times with respect to 1 over T is equal to delta H naught over RT squared. Multiply this by minus T squared to make it look like a derivative. So then we get the derivative of natural log of Kp naught with respect to 1 over T is equal to minus delta H naught over R, because the T squared is canceled out, obviously. Now if we plot this, the natural log of Kp naught by 1 over T, then we get this derivative we just found. Now we assume that delta H is constant, so this is going to be a straight line. If this doesn't end up being a straight line, then delta H is not constant with temperature. If the slope here is positive, that means it's exothermic, and delta H is less than 0. If the slope is negative, then it's endothermic because delta H is greater than 0. So the slope here is equal to minus delta H naught over R, which is what we just found, obviously. Now at very low temperature, then we can say that delta G naught is roughly equal to delta H naught. At very high temperature, we showed that delta H naught is equal to minus RT natural log of Kp naught, which also delta G is equal to minus T delta S naught at very high temperature. So these two are equal to each other also. Continuing on Physical Chemistry, Chapter 6, we're on Section 6 now. So let's talk about shifts in ideal gas equilibrium based on Le Chatelier's principle. One, we're going to look at isobaric temperature change. Isobaric means constant pressure, of course. Now we have the derivative of Kp naught with respect to temperature is equal to Kp naught times delta H naught over RT squared. Now Kp naught has to be greater than 0 and less than infinity. So that means that the RT squared, what the heck, is going to be greater than 0? Oh, okay. So anyway, so delta H naught is going to be what's determined. Yeah, I should have said just and RT squared is greater than 0. So delta H naught determines whether the derivative is greater than or less than 0. Now, let's say we have an endothermic reaction. That means delta H is greater than 0. So the derivative of Kp naught with respect to temperature is going to be greater than 0. What that means is if we increase temperature, then our equilibrium constant is going to increase. Or if we decrease temperature, our equilibrium constant is going to decrease. An example of an endothermic reaction would be that if we take heat plus our reactants to get some product. So if we just increase the temperature, we'll get more product. Now on the other hand, let's say we have an exothermic reaction. Then delta H naught is less than 0. So what that means is the derivative of Kp naught with respect to temperature is less than 0. So that means the opposite of what we had up here. If temperature increases, then Kp naught will decrease, or if temperature decreases, then Kp naught will increase. What we'll have to do then, we'll just have to lower the temperature to get more product. Okay, we're continuing physical chemistry, chapter 6, section 6. Now we're talking about isothermal pressure changes. Remember, isothermal means constant temperature. Let's say we have the reaction reactant A going to product 2B. Now we're going to use Q for reaction quotient. Q is going to be calculated as the partial pressure of B squared, because of the 2, divided by the partial pressure of A, because of the 1. Now we also know that Kp is equal to Pb squared over Pa. Notice these two look the same. Kp, remember, is our equilibrium constant. This is from the concentrations that you would have if you were at equilibrium. This is what you have at any time, including right now. So at equilibrium, Q would be equal to Kp. Otherwise, if we're not at equilibrium, K is greater than or less than Kp. Now let's say that we double the pressure and see what happens. For this particular reaction, Q prime, we're going to say is equal to 2 times Pb, and that's going to be squared, over 2 times Pa, and that's to the first power. So just factoring out, we get 4 Pb squared over 2 Pa, or just 2 times Q. So what happened now is that Q prime has to be greater than Kp. So if we started at equilibrium, so equilibrium is going to go to the left in this case to reduce the value of K prime until K prime is equal to Kp. Now, what that means though, in this particular reaction, is because there were more molecules on the right, more moles on the right than left. So what we're really saying is that we know that Kp is fixed for a given reaction, and it depends on temperature but not pressure. But increasing the pressure then is going to go towards less moles, fewer moles, if you want to get technical. So Kp, we know, is a function of temperature only, but the equilibrium components are compositions of both the reactants and the products. As you can see, it does depend on pressure, so be careful of that. Continuing on physical chemistry, chapter 6, section 6. Now, as an example, let's say we have some hydrogen gas plus chlorine gas going to hydrochloric or hydrogen chloride gas. Now the change in the number of moles is going to be 0. 1 is 2 to 2. So what that means is for this reaction, pressure won't have any effect on the equilibrium because there is no product or reactant side with less moles. Now on the other hand, let's say we go from nitrogen gas and hydrogen gas to ammonia. Now we're going from 1 and 3 is 4 to 2. So delta N is 2 minus 4, or minus 2. So delta N, obviously if it's minus 2, it's not equal to 0. So for this reaction, the equilibrium is very sensitive to pressure. So as an example, we're doing the extent of the reaction against temperature. And we're doing that for several different pressures here. So at lower pressure, the extent of the reaction is down here. Let's do a vertical line here to give you an idea. So at the same temperature, at 1 bar, the extent of the reaction is down here. At 10 bar, the extent of the reaction is up here. And at 100 bar, the extent of the reaction is up here. And that would be true for pretty much any temperature. So what that means is, at higher pressure, we're going to get more product, because in this case, the product has less moles. So we're also at any higher pressure, then we'll also get higher xi, the extent of the reaction. So when they do this for real in industry to make fertilizer or whatever, they use hundreds of ATM. Now, not strictly about isobaric or isothermal pressure changes though, but if we're going to add hydrogen to gas because of the stoichiometric coefficient, it's actually going to shift the equilibrium to the left. And there are people who argue that that might actually be an exception to Le Chatelier's principle. But we're not actually going to go into that right now because you don't need to understand or agree with Le Chatelier's principle to do the math that we did up here. Continuing on physical chemistry, chapter 6, section 6. Now we're going to do an isochoric addition of inert gas. Now remember, isochoric means constant volume, but we're also going to assume that temperature is constant. Now remember, the partial pressure of I is equal to the number of moles of I times RT over V, if you have a perfect gas, which we do. Pi is not changed by an inert gas. I mean, if you can add all the helium you want, it's not going to change the partial pressure of your stuff. So Qp is equal to the product of Pi to the nu I power. So there is no shift in equilibrium. So what this tells us is that adding a noble gas or not has no effect on equilibrium. Now, let's say that we have a reactant gas. Then the temperature and volume are constant. So, we're assuming temperature and volume are constant. That's our first scenario. So A goes to A gas plus B gas, that goes to 2C gas plus D gas. So there's going to be a little bit of change in moles here. So our Qp at any time, remember, is Pc squared times Pd over Pa Pv. Just remember, it's products over reactants. And when we're at equilibrium, that's going to be equal to Kp. Now let's say we add some of A. Well, since Pi equals Ni RT over V, just like we had before, that means adding some A increases Pa. But since A is a reactant, it's on the bottom, that's going to make Qp decrease. So now we have Qp is less than Kp. So what that means is that Qp is going to increase until Kp is equal to Kp again. And of course, for Qp to actually do that, you're going to end up with more products. Continuing on physical chemistry, chapter 6, section 6. We're getting close to the end of section 6. Now, we talk about addition of a reactant gas. What happens if we add a reactant gas at constant temperature and pressure? To understand this, we're going to work through an example. Again, we're going to use nitrogen plus hydrogen to get ammonia. Remember, it's going from 4 moles to 2 moles. For this particular reaction, Kx is equal to 8.33. Remember, X is mole fraction, so that's the mole fraction equilibrium constant. So we're going to start with 3 moles of nitrogen, 1 mole of hydrogen, and 1 mole of ammonia. So remember, our formula for Kx is just the mole fraction of ammonia squared over the mole fraction of hydrogen cubed over the mole fraction of nitrogen. Remember, these exponents come from the coefficients. Now, also, same formula for Q, mole fraction of ammonia squared over a mole fraction of hydrogen cubed over the mole fraction of nitrogen to the first power. So just remember, it's the exact same formula, except Kx is a fixed value for equilibrium, and K is what we have in our system at any time, even if we're not at equilibrium yet. Now, for what we're given, we know that the mole fraction of N2 is just 3/5. Mole fraction of H2 is just 1/5, and mole fraction of N2 is just 1/5. So plugging that in for Q, we get 1/5 squared over 1/5 cubed times 3/5. That comes out to 8.33. Q is equal to Kx, so right now our system is in equilibrium. Now, let's say we add a little bit of nitrogen. Remember, nitrogen is on the bottom here. So we're going to get Q prime. Notice we have to add to the total number of moles. We had 5 moles before, we have 5.1 moles now. So the mole fraction of our ammonia actually went down. It's 1 over 5.1 squared. And then our mole fraction of, what is this one here? This is our hydrogen. That's now it's gone down 1 over 5.1, but that one's cubed. And then our mole fraction of nitrogen, it obviously went up because it's now 3.1 over 5.1. If you evaluate this, we get 8.39. Continuing on physical chemistry, chapter 6, section 6, we're finishing up section 6 now. Okay, we showed before for a reaction, we had an example. We were given Kx equals 8.33. After adding some of the reactant, we got Q prime is equal to 8.39. Now remember, Le Chatelier's principle says that if you add more reactant, you should get more products to counter it. But since Q prime is greater than Kx, the reaction is going to go left, which is what happens in real life. If you add some of the, what did we add? The nitrogen? It went to the left. Yeah, we added some more nitrogen, it went to the left. Now remember, we added at constant pressure and temperature though. If we were adding more nitrogen at constant pressure, this requires increasing the volume a little bit. That, well, we know, will shift the equilibrium in whatever direction has more molecules. The left side had twice as many molecules as the right side. Now, when we do this in industry for real, then we do it about 700 ATM. Also, this is an exothermic reaction, so delta H is less than 0, which means that we want the temperature to be as low as possible to get more product. But of course, remember, we said the reason we need, we can't do it at room temperature is because the rate of reaction would be too slow. So the trade-off there is about 460 kelvins. So what we've shown then is if you have a reaction, delta N of the gas phase is equal to 0, then Kx is just a function of temperature. But if you have a reaction where delta N of the gas phase is not equal to 0, like the reaction we just did, then Kx is dependent on both temperature and pressure. But because solids and liquids are roughly constant volume, we're going to ignore those when we're doing this calculation.